us look at the laws of logarithms. Just as when we did exponents, we had, for instance, a to the x times a to the y gives us a to the x plus y. This is exactly what happens now with logs. If I now take product of a number, then I can use the sum rule just as I did for the exponents. Let us look at an exercise. We have a product, so let us first look at this part. The 3, we just keep it separate. So that log, in this case there is no base, so we assume it's base 10, but it won't change the question if all of them were to the same basis, plus log base log b, minus the rest stays the same. Now I can take my distributive law and multiply the 3 in there, so I get 3 log a plus 3 log b minus 2 log b minus 3 log a. I can see this 3 log a and that 3 log a gives us 0, and then if I add, I get 1 log b. I don't write the 1, I don't write that, so I will just write log of b. And in this case it's base 10 because it did not say. You must always read in the context of the exercise what the base is, because we also have another log which is, we call it a natural log, and you will encounter that in first year mathematics, and that is log the base of e, which looks very strange because e is approximately 2,718 something, and as if it's not very natural, we call it the natural log. That's why we have the L in log natural. But you will use this a lot in first year mathematics, and all the rules that hold for regular logs will also hold for log to the base of e. Here we have log to the base of 2 of 12 plus log to the base of 2, and we can reverse the order. Instead of saying log of xy is equal log x plus log y, we can also do the reverse order, so we can say log base of 12 times 2, which is equal to log to the base of 2 of 24. You can write it like that. And if we have more logs, which we will do now, then we can simplify this further. But for now, it's just the sum rule that we are looking at. So when we divide two numbers like x and y, then we subtract the logs of that. That is similar to a to the m divided by a to the n, which gives me a to the m minus n for exponents. Exactly the same log. Remember, and also the reverse order. The equal sign means from the left to the right and from the right to the left, both of them are true. Let us look at an example. We're going to use the reverse operation, so we're going to say this is log to the base of 2 of 18 divided by 2, and that is log to the base of 2 of 9. Let us look at a new law where we have log base a of x to the m. If I look at the left hand side, I can write log the base of a x times x times x x m times. And if I now use my product rule or my sum rule, then I get m times log base a of x. If we go back to number 3, we had before, from the subtraction rule, we had 18 divided by 2, and that gives me log to the base of 2 of 9. I can now, using this log here, our logarithm, I can now write the 9 as 3 square, and then I can take that 2 to the front, so I'll get 2 times log to the base of 2 of 3. If I look at the next rule, then I see that log to the base of a itself is just 1. Remember, from the definition, we can say that a to the power of 1, this is so if and only if a to the power of 1 is equal to a. So this is what the law says. So if I look at number 4, I'm going to do it here. Log base 2 of 16 minus log base 2 of 2. I can first of all write log base 2 of 16. I can write as 2 to the 4 minus log base 2 of 2. The 4 can go to the front from the previous logs, from the previous law. Then I get 4 log to the base 2 of 2 minus log to the base 2 of 2. That will give me 3 times log to 2, but this is just 3 times 1, which is equal to 3. Or I can say log to the base of 2 of 16 minus log to the base of 2 of 2 equal to log base 2 of 16 divided by 2, that is log base of 2 of 8. That is equal to log to the base of 2 of 2 to the 3. So again, I can take the 3 to the front, so I will get 3 times log to the base of 2 of 2, and that will give me 3 times 1, which is equal to 3. So this is our next law.